Hello, I'm Tim Weaving, a PhD student at University College London, and I'm pleased to welcome you all to the 28th instalment in CompBioMed's e-seminar series in collaboration with the Virtual Physiological Human Institute, or VPHI. The talk today will be given by Dr. La Mattina, a biomedical engineer with a background in signal processing and medical informatics. In 2020, he joined CompBioMed as a postdoctoral researcher based at the University of Bologna to work on fragility hip fracture prevention in postmenopausal women. In particular, he is developing a framework for the simulation of clinical trials for osteoporosis treatments, leveraging high-performance computing facilities. Now, before we begin, I'd like to briefly remind you that the session is being recorded and will be available on the CompBioMed website and YouTube channel shortly. So please do use this to go back over parts of today's talk and others in the series, and maybe even share these e-seminars with your friends and colleagues. There's going to be a Q&A session at the very end of the talk today, so please save your questions until then. Once the talk is finished, you can go ahead and post your questions in the Ask the Staff Questions panel, which is accessible via the question mark icon on your screen, and I'll read them out to Antonino to keep the session running smoothly. Now, that's everything from me. I very much hope that you enjoyed today's talk. And finally, Nino, please feel free to take it away.
Thank you very much for the introduction. Good afternoon, everyone. Today, I'm going to talk to you about the research that is being done in CompBioMed project in neuromuscular skeletal field, especially focusing on femur neck fracture. After a brief introduction on osteoporosis and why it is important to identify patients at high fracture risk and identify them with high accuracy to start the treatment, I will describe the digital twin technology that we have developed, and I will do it with an incremental historical approach, let's say. Afterwards, I will present some derived models that in some way share the heart of the technology, but of course are following completely different and independent development paths. So let's start with the osteoporosis. Osteoporosis literally means porous bones. It is a bone metabolic disease that causes the loss of mineral mass from the bone and the degradation of the microarchitecture of the bone. Basically, how is done the bone? The bone is composed by more or less tightly packed lamellae of collagen. That is a very elastic fiber naturally secreted by our own body. That in this matrix of collagen, there are precipitated crystals of calcium hydroxyapatite. That is the mineral that gives stiffness to the bone. The bone is continuously eroded and reformed by specialized cells. We have the osteoclast that destroy the old bone, and at the same time, the osteoblast produce new bone tissue and slowly deposit calcium hydroxyapatite to reinforce it and make it stiff. Normally, this process is in equilibrium, especially in the young population, in young groups. But in elderly people, the balance between osteoblast and osteoclast is broken, and the mineral content starts to decrease. This imbalance is especially severe in postmenopausal women, where the metabolism is altered by the changes in of the hormone due to the menopause, basically. So what happens is that as the woman ages, the bones become more porous with the trabeculae of the spongious bone that become thinner. The cortex is also becoming thinner, and definitely the bone becomes more fragile. Fragile at the point that normally harmless fall can cause fractures. The typical sites for the fragility fractures are wrist, ankle, ribs, can have fractured vertebrae, but the most catastrophic for the patient are for sure the fracture of the proximal femur, because the treatment of the femur fractures need to deploy some kind of prosthesis, such as nails or screws, or totally replacement like the one showing the figure on the right. The procedure indeed is very invasive and painful for the patient, and also the recovery from this kind of injury is very slow. In addition, a lot of time the patients will never recover an original quality of life. So we have a very high cost for the health insurance, national health system. Also because the patient needs hospitalization, rehabilitation, and because it will never recover its independence, it will need the continuous medical assistance from nurses or family members. The total impact of its fractures is increasing with the continuously aging population, and every year it's estimated that more than 20 billion euro are spent to treat more than 600,000 hip fractures. 1/5 of the patients that experience hip fracture actually dies within 1 year. And as said, most of the survivors will live with reduced mobility and reduced independence for the rest of their life. This event is catastrophic, but fortunately is not so frequent if we look at a certain population. So if we take some patients and we monitor them, only 5% of the fallings will actually cause fractures. That's why clinical trials that try to use as a clinical endpoint, actually the recorded fractures, need to enroll thousands of patients and observe them for a time span of several years to record a sufficient number of fractures and demonstrate drug efficacy. There are also very rare fractures that are not due actually to a fall, but they need a combination of extremely fragile bones and extremely compromised muscle control that causes abnormal load on the femur. This is called spontaneous fracture, but we are not treating them a lot because they are very rare and they need very specific circumstances to happen. So what can be done to prevent these fragility fractures? Currently, there is no cure for osteoporosis. We have only a handful of drugs that can slow down the mineral loss, and sometimes they can also temporarily invert the trend, so they make the bone have more mineralized tissue than before, but only temporarily. To start the therapy, because like every drug, there are side effects, we must identify the patient at high risk, and you need the way to define and to measure the osteoporosis level and the trend of this in the time. The World Health Organization identifies and classifies osteoporosis with a so-called T-score. What is done basically is done a kind of radiograph. It's called dual energy X-ray absorptiometry. Basically is a two energy radiograph that is able to separate the mineralized tissue from all the others of tissue, such as muscle and fat. So in this way, we can estimate the mineral content of a certain region, and by dividing it to the projected area of the bone, we can estimate the so-called areal bone mineral density. Usually this is done on the proximal femur or on the lumbar vertebrae. The recorded value is then compared with the value that is found in a reference young healthy population that usually is women between 20 and 30 years old. And the metric used is a T-score, that is the number of standard deviations that separates the measured value for the patient and the average of the young population. Specifically, there are two defined thresholds. One is -1 and the other is -2.5. Patients with T-score above -1 are considered at low risk because they have a mineral content that is more or less the same as the young healthy population, while patients that have a T-score below -0.2, that for the young population is less than 0.5%, are considered at high risk because they have a fragile bone because it's not very stiff. Of course, when the population ages, this Gaussian is shifting towards lower T-scores. So we have a situation like this. And for the patient at low risk, we do basically nothing and wait and monitor them in the next years with another scan. Patients at high risk are given some medication to mitigate the effect of osteoporosis, but there is this gray area in the middle in which there is no default treatment until today. The problem is that this classification based on DXA has a limited predictive power, and almost half of the 8 fractures happens in women that are not officially diagnosed with osteoporosis. So the researchers started to look for new technique to estimate the fracture risk with a higher predictive power, in order to allow this early and precocious identification of patient at risk and promptly start a therapy. A possible solution developed is the development of subject-specific finite element models that are informed with quantitative computed tomography. That is a kind of calibrated CT scan in which we can in some way relate the gray level of the CT scan with the mineralization of the tissue and so the stiffness of the tissue. These models use the CT scan to extract bone geometry and estimate the local material properties of the bone. And we obtain in this way digital twin of the patient bone on which we can run different simulation scenarios without the need to have a reference population to identify thresholds, but we can base all of the work on mechanical physics law. So let's start with a brief history of the development of this digital twin in the CompBioMed project. There was some work done before the beginning of the project by lots of research teams in the world. Among them, the group of Professor Viceconti at Rizzoli Orthopedic Institute that developed the workflow to predict the femur strains on cadaver femurs with finite element models. The workflow was extensively validated with controlled experiments in the laboratory, and at the end, for the strain prediction, they obtained a correlation coefficient higher than 0.9. The model was also able to predict the femur fracture load and the position of the fracture with pretty high accuracy. So before the start of the CompBioMed project, we already have a digital twin of an ex vivo controlled experiment with carefully controlled boundary conditions. In CompBioMed, this workflow has been applied to living patients, for which there are a lot of parameters that were not controlled like in the experimental test. In particular, for the validation of this model, it was developed the so-called Sheffield cohort. That is a cohort of proximal femur scan collected at the Sheffield Osteoporosis Center. The cohort is composed by 98 postmenopausal women divided into two subgroups. 49 women had a proximal femur fracture already in place at the time of the CT scans, while 49 were not fractured at the time of the CT scans. This cohort was pair matched, so the women with fracture and without fracture were paired one by one in the sense that they had the same age, height, and weight. The cohort is retrospective because at the time of the scans, all of the data were already known about the patient, and the patient were already fractured or not fractured. For each patient, we have the DXA scan, the proximal femur CT scan, and also the answer to the FRAX questionnaire. There is another epidemiology-based questionnaire for the prediction of femur fracture over 10 years. As we can see, the population was largely osteopenic, with some very severe osteoporotic patients with a T-score of -4. To evaluate the performance of the classification of the algorithm that we were developing, we used the receiver operating characteristic curve. That is a curve constructed point by point by recording the true positive rate and the false positive rate by varying the threshold that we are using. This curve, especially the interior of the curve, that is called the area under the curve, gives a global indication of how much the subpopulation of fractured and non-fractured subjects are well separated by the classifier, regardless of the threshold that is actually used at the end. The IDRA classifier has an area under the curve of 1 because it correctly identifies all the fractured patients and discards all of the non-fractured patients. On the contrary, a completely random classifier has an area under the curve of 0.5 That is like tossing a coin and decide if the patient is at risk or not. All the other classifiers stand somewhere in between these two values. In particular, Femur net score for the Sheffield cohort has an area under the curve of 0.75. So at the beginning of CompBioMed, we are here. We have a model that predicts with extremely high accuracy the strains on cadaver femur, with a pretty high accuracy the strength on these cadaver femurs, but at the beginning it performed as good as T-score when used on the Sheffield cohort. So the first step for the refinement of the model was the use of an anatomy atlas to estimate the right orientation of the femur with respect to the patient body, because as said in the Sheffield cohort, we only have proximal femur CT scans, so we do not have the entire shape with the knee. And so this anatomy atlas was used to correctly orient all of the femur, and the simulation was not done only on a single condition, but a span of angles for standing and falling condition was used. And the worst case that was usually found in the falling was used as a predictor of femur fracture. With this change in workflow, the area under the rock curve increased to 0.79. So this idea of spending a range of possible impact angles was maintained and further developed. The next step was the definition of less idealized boundary conditions. So the anatomy atlas was not only used for the orientation this time, but also for the estimation of the location of the knee rotation center. In the new model, the femur is free to rotate around the knee center and impacts an inflated rigid floor, let's say, with a non-linear surface-to-surface contact. Also, it is expanded the span of the simulated impact angles to include also the posterior angles in order to explore the entire surface of the greater trochanter. With these improvements, the accuracy of the digital twin increased to 0.82. Another jump was done with the inclusion of the stochasticity in the size wall model. The underlying idea is that actually we don't know how each patient will fall in the next 10 years. So instead of trying to precisely simulate each of these single falls, we try to take into account a wide spectrum of possible fallings and in some way summarize the result in a single number that we call absolute risk of fracture at time zero. In this simple multi-scale model, the patient body is idealized as an inverted pendulum, and for which we sample with Gaussian distribution the starting and the end angle when he impacts the floor, the starting velocity and acceleration of the center of mass, and damping factor due to clothes, the floor characteristics on the protector. And in some way, we try to take into account postural defense. These latter parameters tries to in some way capture in a very simplified way the fact that the patient is not falling as a pendulum and an animate object, but in some way try to bend the knee or grasp some object or slide against the wood wall to slow down the fall and mitigate the impact. So at the end, we have 6 Gaussian variables that are informed by literature research, and this model is combined with patient characteristics and the impact angles alpha and beta that are the 28 angles of the previous described model. So basically what we do is we estimate the critical loads with the 28 nonlinear models and compare the critical load with all of the possible impact loads of the multi-scale model. If the impact load is higher than a critical load, then we record that fall as fracturing. Otherwise, we record it as no fracturing. Then we average everything with a Monte Carlo scheme integration, basically, and we obtain the absolute risk of fracture at time zero, or briefly ARF0. This other stochasticity increases the model accuracy up to 0.85, so we reach the level of accuracy of the strength of cadaver femur. The last step, up to date, because everything is still in development. So the last step until now in model personalization is performed by using soft tissue thickness, not by fitting a linear fashion with the patient body mass index, but actually measuring the thickness of the soft tissue in each direction of the fall from the CT scan. This requires, of course, an additional step in the modeling phase, because we have to segment also the soft tissue or the air surrounding the body. And to do this, of course, we need that the CT scan has a sufficiently large field of view to correctly segment the soft tissue. This small difference in the workflow gives us another 2% of precision of the model. So here we are. This is the current workflow of the digital twin for patient fracture risk estimation. That is called CD2S, that is computed tomography to strength in Sheffield, and BBCT, that is Bologna Biomechanical Computed Tomography in Bologna. The steps are the same. So we start from the CT scan. We extract the three-dimensional geometry of the femur and some anatomical landmarks for orientation and knee center rotation. And then we create the three-dimensional mesh. We assign material properties for each element depending on the local gray value. And we run the 28 simulation, usually in an HPC environment, to make suitable the parallelization of all the simulation. We obtain a critical load map, and we compare each critical load with this 1 million of possible patient-specific falling loads to obtain the ER0. News of the last days, we now have the material mapping program written in Python 3, so it's portable and is already being tested on some HPC center. We are working now on the parallelization and scalability of this program. Before now, we were using a program that was only developed for Windows platforms. So this was hindering us from the complete automatic execution of the workflow on an HPC system. But now we have it in place. So once we have the geometry and the landmarks that until now we have to perform it manually or semi-automatically, everything can be run in automatic in an HPC center with basically no input from the user. The simulation of because of course the large part or the automatic part, the large part of the time is the simulation of the fall angles, and it requires from 50 to 100 core hours per patient, depending on if you only model the proximal femur or the entire femur. In Bologna, we are currently working on the validation of this pipeline, also on another cohort that is retroprospective, because the cohort is composed by 101 women with an age over 55 years. And on these women, 4 experienced the proximal femur fracture after the CT scan within 5 years. So it is retrospective because we already know who is fractured and who is not, but it's prospective because at the time of the CT scans, no one was fractured, and all of the fracture happened after the CT scan. So what we are estimating now is actually the prediction of accuracy of the model, and not the stratification. We are not separating who is already fractured from who is not yet, but we are differentiating from who will fracture and who will not. The CT scans were originally collected at the Ritual Institute for the preoperative planning of hip replacement for osteoarthritis or hip deformities, but we use obviously the contralateral healthy femur side for the model. We are also requesting to the European Medicine Agency a qualification advice to use this workflow as a surrogate of fracture risk instead of DXA in early clinical trials to estimate fracture risk. On the other hand, in Sheffield, the team worked to bring this technology nearer to the clinicians and to make it more accessible and easy to use for the clinicians that are at the end users of this workflow. Everything can be done only in research setting because we would need the CE mark to use it in a clinical setting. But basically, in Sheffield, they developed a Django-based web app to manage the request of the analysis of a CT scan. So the clinician has to anonymize the image and request with the web portal the simulation of the patient. And there is an operator inside the University of Sheffield that has no access to personal information of the patient, and he normally runs on the simulation, and at the end gives the clinician the results of the analysis in a very simple way as seen by the clinician. The core of the application is the background communication between the software components that allow this data transfer between the hospital and the university network in a safe way. So the clinician transferred the pseudo-anonymized CT scan from the hospital PACS to the university XNAP server and inputs the patient code in the metadata of the job request. Then the CT2S web app scans the XNAP server and searches for the image, copies it into the HPC cluster of the University of Sheffield that is called Shark. And from there, the operator can download the image, run the analysis, and send the results back also via the CT2S web app. The clinician is notified via email for all of the steps of the simulation. So you know when the job has been validated, when the job is assigned to an operator, when the analysis is finished, if the analysis was successful or it failed, and so on. So from the point of view of the clinician, he has to copy this image and to fill in a very simple form on the web. And after a bunch of hours, that depends on how much is busy the HPC cluster, basically, he receives a complete report of the fracture risk of the patient. In the, for the clinician, best case of 3.5 hours, almost half of the time is due to the segmentation of the femur. It is done still manually or semi-automatically. So if we manage to cut down this time, we hope to cut down the time to 1 hour or even less if we have a completely automated workflow and the operator only have to check if the segmentation is done in a correct way and everything is done smoothly. Another branch of work involves the use of internal references to self-calibrate the CT scan without using an external phantom. Because right now we use an inline, such as in the image, the Mandwave phantom that is under the patient, or an offline phantom scan to calibrate the CT scan and to know at each gray level which is the mineral density of the tissue that is in that voxel. We are exploring the possibility to use hair, fat, urine, aortic blood on skeletal muscle to self-calibrate each image. In this way, we can also use all the CT scans for which we do not have a phantom to calibrate them. We currently are working on the validation of this method on the ritual cohort to investigate how much the change in the calibration method will influence the prediction accuracy of the model. And that's it for the digital twin technology. Now I will describe some derived model, let's say, and I will start from the implementation of an In Silico trial for osteoporosis drug. That is what I'm currently doing in Bologna. So as we said before, phase 3 clinical trials that need to demonstrate the efficacy of the drug are very expensive, both in terms of time and money, because they need to enroll thousands of patients and they need to monitor them for 5 years at least to reach statistical significance with an acceptable number of fractures recorded. Our idea is to use simulations to speed up the development phase and, for example, try to identify which are the best population on which to run the actual clinical trial, or we can enrich the simulation with heavier tails so we can explore what happened to rare condition of the patient and so on. So our idea is to apply the same workflow that we are developing, so C2S for BBCT, to the entire population. The code name of this application is bone strength. So BBCT or C2S are the digital twin, while bone strength is the In Silico Trial solution. To run the In Silico Trial, we need a bunch of things before. We need a very large virtual population to capture the patient variability in terms of both shape and stiffness of the femur, but also we can think about capturing the variability of the lifestyle of the patient or the compliance with the therapy, if possible. We also need a model to describe the physiological aging process, in which bone is losing mineral mass in a physiological rate. We need a disease model in which some of the physiological parameters has been impaired and changed, and in our case can be that the osteoclasts are too much active, so they are destroying the bone faster than normal, or that we have a less active osteoblastic, so we are not creating new bone fast enough to balance the destruction of the osteoblast. To run all of these models together, we need an adequate compute power that usually we are using HPC center to have it in a reasonable amount of time. To have a large cohort of subject to run the simulation, we have fundamentally two choices. Or we obtain real patient data, so we have to actually segment 1,000 or more CT scans to have enough femurs to run the simulation, or we can create synthetic models in some way. One way that we explored is the creation of a statistical anatomy atlas based on principal component analysis. This was created in collaboration with Professor Mark Taylor from Flinders University in Southern Australia. And basically, we took a subgroup of the Sheffield cohort, so 94 femurs, that were also in this case paired, 47 fractured and 47 not fractured. And it was created one high quality mesh that was the mesh of the median femur. And this mesh was morphed to fit the other 93 femurs. For each femur, then there was done the mapping of the material properties on each element, and at the end there was done the principal component analysis on node coordinates and element stiffnesses. We obtained in this way a synthetic representation of the population, but the measure was not compact because we need more than 70 modes of variation to describe 95% of total variance. So at the end, we decided to use the entire 93 components generated by the atlas. So now we have this representation, and we decided to use this to synthesize new patients with the statistical aliasing of this principal component. So we are oversampling the distribution of the principal components to obtain new patients that are not real patients, but should have biomechanical characteristics comparable with that of the population from which we started, that is the Sheffield cohort. Because some of the components were not actually Gaussians, especially the last one, we used inverse transform sampling to extract random numbers with exact same distribution of the original principal components. So for our IRF0 workflow, we also needed patient height and weight, and we assigned them randomly based on body mass index regression with the iron bone mineral density of the Sheffield cohort. We created 1,080 synthetic femurs, but of these, only 1,044 were suitable for the simulation because Some of them had some excessive mesh distortion that were preventing model convergence in some simulations, or for some pathological cases, let's say the model was too distorted to be simulated in any way. So by comparing the minimal sulfur strength and the absolute risk of fracture of the original and the synthetic cohorts, they appear to be quite similar, and importantly, they are not statistically different. Also, if we use the optimal thresholds that discriminate the fractured and the contour subject in the original population, these thresholds still divide the synthetic population in two parts that are more or less with the same numerosity. So we can conclude that the biomechanical characteristics of the population are preserved by this oversampling workflow. As regards the aging model, we started with a very simplified approach. So we had this morphed mesh that were used for the statistical anatomy atlas, and we extracted the mineral density of each element and tried to relate them with the variable mineral density on the cohort of the patient that were used. The elements were divided into three categories, with high, medium, and low mineral density. And for each category, we searched for a single fitting slope for the linear relationship. The underlying idea was that extremely low density elements contain basically no mineral tissue because they are bone marrow. So in that elements, there is almost no bone remodeling. While for the medium and the high density, we have a bone remodeling rate that depends on the activity on osteoclast and osteoblast. And this activity, our hypothesis is that it depends on the bone-free surface. So in the medium density elements that are made of porous bone, there is more void. So we suppose that in these elements, there is more bone remodeling than in the high density elements, which are cortical bone that is more compact and there is less void and less space for the cells to go there and remodel the bone. So in this way, we created the phenomenological aging model that links the local mineral density of the elements with the global mineral density of the proximal femur, without any reference to the underlying biological parameters. We performed a systematic review on the placebo arms of the past clinical trials to estimate the variable mineral density loss during a time span of some years, between 3 and 5. In the next future, we will work on the creation of biological informed models, and we will explore basically two different paths. The ordinary different equation, or agent-based, in which we model the actual single cell and how the cell is interacting with the other cell and with the environment. And want to do this to simulate the activity of the cells in the bone remodeling and to expose some intervention point that can be influenced with an external stimulus that can be quantified, like such as the use of a drug that is inhibiting some metabolic pathway or something like that. Whichever modeling approach that we will use, we do not expect this to cause an explosion in the compute power needed, because either the ordinary differential equation or the agent-based model are already pretty parallelized on GPUs. So all we need will be an efficient coupling between the different model scales, but the time of the simulation should not increase a lot by using this. This work is still in the embryonal stage. We are not starting yet to develop this model, but that's what we'll do in a couple of years, let's say. Done this, we have also to do a bit of a change on how we think this simulation, because the current digital twin workflow, if we want to apply it as it is to a cohort of 1,000 patients, and run it 2 times, one for the placebo or the comparator arm and one for the treatment, and do it for 10 years, will require a couple of core hours, a couple of million of core hours, more or less. That on the upcoming computer Leonardo that will be inaugurated tomorrow in Bologna, it will need, with the entire supercomputer doing this, which will require almost 1 day. Also, the output that we will have in this way is a fracture risk for each patient. But what is recorded in clinical trials is actually the number of fractures within a certain observation time. So we have to change the way we run the simulation. So we started developing a Markov chain version of bone strength. What are Markov chains? They are stochastic processes in which the future state is depending only on the current state, regardless of the history, and some random input. In our case, we define a fall probability for each patient, and for each time step, we decide if and how many times this patient will fall. For each fall, we assign a set of random parameters as in the IRF0. So we're not simulating 1 million of fallings and then average the results, but we are actually simulating one falling and see if that falls is breaking the femur or not. If it's breaking the femur, okay, the patient goes out of the simulation and we record this fracture and the time. Otherwise, we will go to the next time step. If needed, we update the material property and we make the patient fall again. We have to run some convergent tests to have robust results. One is that we have to be sure that we are sampling the time step with fine enough to collect all of the variation of the material properties. We run the simulation and we have that over 200 patients, only one changed the fracture year. So we concluded that 1 year is okay as the time step. And the other thing that you have to do that is a bit more tricky is that as everything is stochastic, every time that we run the simulation will be different because different patients will fall. They will fall a different number of times with different parameters. So for this, we run the simulation on the original 94 patients with 1 year bone loss time step, and we run 25 realization. And here, what we do is we average the number of fractures cumulatively. So we start with taking only one realization, and then we use 2 realization and do the average and the standard deviation, and then we use 3 and then 4 and then 5 and so on, and we stop when the coefficient of variation is not changing more than 10%. In this case, we obtained it after more or less 15 realization. So with some times of simulation, maybe we have stable results, but it is still work in progress. Also, to validate this, we need the past clinical trials from the literature, and such the comparison, we are currently overestimating the number of fractures. So we are working on a better estimation of the stochastic parameters of the model, especially that regarding the force transfer model between the ground and the bone. Also, the fact that we have a population that in which half is already fractured can be a bias for this simulation. So we plan to create a new statistical atlas with a ritual cohort and test again all of the simulation to see if something is changing or not. Another development branch involved the integration with neuromuscular control. That is, that personalized model can be created not only for the bones, but also for the muscles. In this case, in Sheffield, they collected CT scans and magnetic resonance scans of 5 women and constructed bone and muscle models. They collected also gait analysis during level walking, and they estimate the activation pattern of the muscle to have that motion of the patient. That is called the inverse approach. So from the kinematic to the activation of the muscles. Then they applied the force of each muscle on the bone as a boundary condition for the finite element model. The gait cycle was divided into another interval, and for each time interval, there was estimated the optimal muscle activation pattern. I say optimal because actually the problem of model activation pattern is undetermined, because there is an infinite number of configurations that can lead to the exact same kinematics. What is done is that is defined the cost function that for the optimal control is the minimum activation, the minimum of the sum of the activation of the muscles. But in elderly patients, actually they are not using an optimal control, but they are suboptimal, because due to nerve damage or osteoarthritis or some pain, the patient is not using the optimal approach, but is activating some muscle that usually should not be activated, and so on. So for each time step was estimated the linear finite element model, and were extracted the first, so the tensile and the compressive principal strains. And a high correlation was found between the first principal strain and the gluteus medius force. The discovery of this correlation can lead to the personalization of the rehabilitation of the patient, for example, because if you know that some muscle is giving an abnormal effects on the principal strain of a certain part of the bone that is very fragile for the patient, we can teach the patient to use less than that muscle and activate other muscle instead of that to reach the same motion, for example. Or we can try to minimize processes wear depending on the joint load due to the muscle activation. To run these massive simulations, we need an efficient way to simulate the human movement. As I said, neuromuscular control is not always optimal, especially for elder patients. And there are two current big challenges in human movement biomechanics. One is the prediction of the actual recruitment strategy that the patient is using, because it's not optimal usually. And the other is the simulation of forward dynamics, that is, knowing the activation of the muscle, predict which will be the kinematics. The solution of the forward kinematics in a very short time, the long-term goal, very long-term, is to have them in some fraction of seconds, will enable the use of walking exoskeleton for patients with spinal cord injury. To solve this problem, we are not actually doing this by ourselves or in first person, but we are like monitoring what's happening in the world. Quantum computing can be a very promising path. In particular, there are some experiments done on the wave system for the suboptimal prediction control, and they show a 1,000-fold speed up on a simplified muscle control problem. So this dramatic speed up could enable this technology. Of course, we will need a very clever and efficient couplers. Finally, I will present some extension of the workflow to slightly different application and slightly different bones. These models are still in development stage and are undergoing the validation of what was done 20 years ago for the femur. One is the intraoperative femur fracture. These are fractures that happen during the total hip arthroplasty while the surgeon is inserting the prosthesis in place in the femur medullary canal. And the surgeon does this with the help of a hammer. This type of failure has a relatively low incidence because it happens only in a few % of the cases, but is highly design dependent. In particular, in the Emilia-Romagna register, there is also the Research Institute, we have the highest and the lowest intraoperative fracture rates for prostheses of the same company. So we talked to the company and we are developing with them a platform to simulate the risk of intraoperative fracture before the stem is even produced the first time. Using a very simple approach, basically the starting of the workflow is the same. So we segment the femur geometry, assign the material properties, and we perform a Boolean subtraction with the rasp, that is this cutting tool used to create the hole. Then the stem is put in place with the size and position decided by an expert surgeon of Research Institute. And we start to insert this femur. So we apply 1000 Newton, and we check if some elements are exceeding the critical tensile strain. If these elements are too much deformed, we kill them, and we keep the load constant and allow the strain redistribution. And we repeat this test and kill process until no more elements are exceeding the limit. At this point, we increment the load, and we do this test and kill process again and again and again. The simulation finishes when there is rigid body motion of the stem, or we have some excessive distortion of elements, or when we reach 10,000 newtons. With this very simple approach, we are obtaining reasonable crack propagation in the models, and the cracks often reach the external surface in location comparable with the intraoperative fracture reported in literature. Still, we need to validate the model with the experimental or epidemiological data to identify the fracture in an automatic way, because right now we are inspecting the simulation, deciding if the femur is fractured or not. The simulation is quite compute intensive and requires a lot of I/O because on how the finite element program is working. So the problem is that to have an in silico trial for this platform, we need to run a lot of simulation. We plan to use 11 femurs collected from Riccioli, and we will use their original material properties, and we simulate 3 degrees of osteoporosis to account for the anatomo-densitometric variation in the population. And to simulate the surgical variability, we want to use the nominal size of the stem and the sides right after, right before, and to perturb a bit the orientation of the stem. Just with this simple model, we will obtain 700 finite element model to run that will require more or less 150,000 core hours for each stem design. And if we run a full Monte Carlo approach, this number will explode dramatically. Also, we want to apply similar approaches to other types of failures of processes, such as massive wear or aseptic loosening. On a completely different body part, we are working on the finite element modeling of vertebrae. Here, the main goal is to provide the clinician a tool for the assessment of the vertebral fracture risk in patients with osteoporosis or with vertebral metastasis. Here we are at the early validation stage, and we are using digital image correlation. That is a technique that gives a full field of the displacement on the surface of a body. And what we are doing is that we are creating the finite element model of the experiments. And here, great importance for the validation is the definition of the correct boundary conditions and the registration of the data of the CT scan from which the finite element model is developed, and the DIC measurements that come from the instrumentation. The results are a very good agreement between the experimental and the simulation, both quantitatively and qualitatively. And the correlation coefficients are over 0.9 on all the displacement components and total displacements. For the use of this model for metastasis, the problem is that we have 3 types of metastasis that are lytic, blastic, and mixed. In the lytic, no problem. Basically, the bone tissue is substituted by some low density and low mechanical property tissue. So if it's darker, there is a lower density, there is a lower stiffness. The blastic are trickier because the mineral tissue is substituted by highly density tissue, but this tissue is not guaranteeing the mechanical property of the healthy tissue. At least this is not visible in a clinical CT scan. To do so, we can use a micro CT. That is an X-ray tomography technique similar to the CT scans, but with a much higher spatial resolution, or some microns instead of some millimeters. In this way, we can see the single trabecule, and we can run a voxel-based model. And just by using linear hexahedra, we have more than 105 million degrees of freedom. We need a lot of RAM. The simulation time is not extremely high in this case because the model is linear, but the RAM consumption is extremely high, and this can be useful to create a material model for the metastasis to inform the clinical CT scan. Because of course we cannot use this imaging technique in clinical settings because it delivers a very high dose of the radiation to the patients. So to conclude, we developed the digital twin for the estimation of the proximal femur fracture risk. The workflow is pretty mature and now it's deployed on several HPC clusters in Italy, in England, and in the Netherlands. And this can be used by clinicians for research purposes. On this technology, we are developing also an In Silico Trial platform for osteoporosis drugs. And we are starting to include the muscle forces for a real-life stress test of the bone to model the effect of the suboptimal neuromuscular control. And we are also developing other finite element models based on CT scans, but we are still in the early validation phase for this. And I wish to thank all of my colleagues and co-workers and supporting and funding institution, and thank you for your attention.
Thank you very much, Antonino. Just a quick question for the, a quick reminder for the audience that if you have any questions, then please navigate to the Ask the Staff a Question panel, which should be accessible via the question mark icon on your screen. It should look a little bit like this one that's being shown on the slide here. And you can go ahead and type your questions in there so that I can read them out for you. Now, during the talk, we actually got one from Matteo Mascagni, and I mean, I think you've probably just about covered this, Nino, already, but I thought I'd ask it just in case you wanted to talk about it in any more detail. But the question was, what are the current computational high-performance computing technological limitations, and what do you need in computational terms in order to achieve your next goals? I mean, I know you mentioned a target of 200 milliseconds for various simulation tasks. But what are the main obstacles that need to be overcome in order to achieve that?
Oh, thank you. For that, the problem is that the program that we are currently using, that is OpenSim, was originally developed for Windows platforms, and just the installation on a Linux cluster is a bit painful. There's a lot of dependencies, problems, and compatibility. And in theory, the equations should be ordinary differential equation and algebraic equation, so they should be suitable for GPU accelerators. But until now, I don't think that there is a GPU version of that software. So basically, we are waiting for an optimized version of that software, and then we will work, of course, on the integration with our models. And also for the quantum computing is still in very early development. That the data that I showed before about the 1,000-fold speed up were done on a 2 or 3 muscle model. Only in the leg we have like 20, 30 muscles. So the computational complexity is really very high in this case.
Oh, absolutely. I'm in research regarding quantum computing myself, so I'm very aware of the difficulties that are present there. What other questions do I have? So one that I wanted to ask is regarding the Femur impact model that you presented there, because of course in reality patients might, for example, use their hands to soften the landing, or there could be other external factors that interfere with the fall. So does your model account for that, or is it intended more as a worst case scenario in which the fall is unimpeded?
Yeah, actually we try in some way, very simplified and very brutal way, to take into account by using a coefficient that is basically reducing the impact force that is acting on the femur. Like at maximum, I think that we divide the force by 2 basically in the best case for the patient, let's say. But of course, this is one of the parameters on which we are working to try to lower the risk of fracture that we are obtaining now for the In Silico Trial simulation, because this parameter is very brutal. We may try something like a multi-body simulation, maybe to see if we can obtain something more reasonable. But as the first step, we will maintain this simple approach, I think, and try to tune the magnitude of this damping coefficient to see if it's enough, basically, to reach a reasonable number of fractures in a certain time. But yeah, absolutely, it is a very brutal simplification of the model, and we are aware of that. But we still have to think in a clever way, also because for young patients, it's straightforward to think that they have good reflexes to try and do something to mitigate the falling. In elderly patients, we don't know the reaction time. Actually, we are now trying to do some math to estimate the falling time and compare it with the reaction time of the elderly to see how much this can be, let's say, impactful for the simulation.
Right, I see. Thanks very much for your answer. I had another question for you, and this one is concerning healthcare in general. So, I mean, healthcare systems are generally very well established, and therefore, new adoption of the adoption of new technologies can be quite slow. So, what I was wondering is, have you had positive responses from clinicians or regulatory bodies who wish to adopt this sort of simulation in their existing practices?
Yeah, in Sheffield, the platform is in place, and it was defined actually with the clinicians. So in Sheffield, they already have something in place, and I think that they are having good feedback from the clinician. In Bologna, we have another project that is called AMET3B, and we want to, in some way, federate the research hospital of Bologna, of the city of Bologna, with the university and with the National Supercomputing Center, to have this network in which we can share safely the data of the patient. And actually, we have a couple of requests of clinical trials in which to include as a say the side product also our pipeline to validate it against real data in a prospective way. So I think that clinicians are responding pretty well, also because this is not requiring a lot from them. We are only requiring them to give us the CT scan of the patient and some basic biometric data such as height and weight. So for the clinician, it's very low effort, and I think that they like and they need this support from us.
Okay, I see. Thank you very much. I haven't received any further questions from the audience, so I think this is probably a good point to start drawing the session to a close. Before I do that, I just wanted to draw attention to the EU funding, which we're very fortunate for, part of the Horizon 2020 Research Innovation Programme. You can see the grant number is visible at the bottom left of the screen there. So just before we finish, I'd just like to take a moment to plug CompBioMed's free scalability service here. So if you're someone who uses or even develops biomedical applications that necessitate intensive computation, but say you're running into performance issues that are limiting the scope of your research, then CompBioMed offers a service completely free of charge to improve the turnaround of your computing jobs. Next slide, please. So if this is something that applies to you and your research, you can go ahead and fill out an application form available on the web page displayed at the top of this screen. Or otherwise, please feel free to reach out either at the email address shown here or via the In Silico World Slack channel. Next slide, please, Nino. So In Silico World is a community devoted exclusively to in silico medicine, offering expertise, opportunities for collaboration, and also a safe space to exchange ideas and advice. Next slide, please. So already In Silico World has a large following, including members from large biomedical companies, biomedical SMEs, independent software vendors, clinical research institutions, and even regulatory and standardization bodies such as the FDA and NICE as well. So that's all I wanted to say there briefly. So before we wrap up, thank you once again, Nino, for giving us your time today. A reminder that this e-seminar will be available on the CompBioMed YouTube channel and website. Finally, a huge thank you to everyone in the audience for attending, and I very much hope that you enjoy the rest of your day.